radical equations. How do we solve equations that have radicals within them? We know if you have a square, you can get rid of the square by taking a square root. But now what happens when you have the root and you have to go back and try to find what the value of x is? So as we go through and solve this, what's one thing you think you could do with this particular problem?
Add the 2 to the other side.
Add the 2 to the other side. That's probably a good place to start. If we add the 2 to the other side, we are isolating the term that has the x involved. The term with the x is this first one, which is the cube root of x minus 5. So if I add 2 to the other side, my equation now becomes the cube root of x minus 5 is equal to 4. Now there's another way you could write that problem. You could think of it as x minus 5 roots are in the denominator of a fractional exponent. So x minus 5 to the 1/3 power is equal to 4. That's the same thing. I don't care which way you look at it, but how do you get rid of a cube root?
You square it.
You cube it. If it were a square root, you would square it. If it's a cube root, you're going to cube it. So if I cube this side, if I cube the left-hand side, I have to cube the right-hand side. Now, if you look at it in the other format, which the cube root means to the 1/3 power, if I talk about cubing that, when you take a power and you raise it to a power, what do you do to the exponents? No, you don't. You multiply them together. What's 1/3 times 3? A number times its reciprocal is 1. So this leaves you with x minus 5. But you have to cube the other side, so that's equal to 4 cubed, which is 64. So we come back over here to this method that I have over here. We know that a cube and a cube root are going to cancel each other out. So we get x minus 5 is equal to 64. And then I go ahead and add 5 to both sides. And you get x is equal to 69. But you always have to check yourself because the original problem has a root involved. And when you work with a root, you want to make sure that you don't get a complex number in your solution, which is a good possibility. There might be a possibility that your answer is no solution. So if I put this back into the original problem, you are going to get the cube root of 69 minus 5 minus 2, and they tell you that's equal to 2. Is that a true statement? 69 minus 5, you're going to take the cube root of 64, subtract 2, does that equal 2? The cube root of 64 is 4, 4 minus 2 is 2. Therefore, you go back in your solution saying x is 69 is a correct solution. But the key thing is don't forget you have to check yourself. You have to check yourself. If you look on page 53 in your textbook, though, those problems are a little more complicated. This one, the example we just worked through, had how many roots? One term. One term that's a cube root. If you look on page 53 of your homework assignment, you look at problems 8 and 9, and what happens? Oh, I have 2 terms that happen to be roots. So how am I going to solve through a problem that has 2 radicals involved? When we think of it, how do we get rid of a cube root? You cubed it. How do you get rid of a square root? You square it. So some of you might think, well, the last time I moved the constant over to the other side and kept the radical on one side. My radical's on one side, so I'm just going to go ahead and I'm just going to square this. What does it mean when you square it? Multiply it times itself. So it just doesn't turn it into s minus 48 plus s. You can't just get rid of the radicals in both terms. You square it, which means you take it times itself. And if I were to do that, you're going to get something that looks kind of complicated. What happens when you multiply the first times each other? You get s minus 48. That's not too bad. But if I multiply the outer together, You're going to get plus the square root of, when you're multiplying radicals together, what's the square root of 3 times the square root of 2? Square root of 6. You multiply the radicand values together. If I multiply the radicand values together, since they are different, it gets complicated and it looks something like this.
Well, you gotta square that.
Then if you multiply the inner together, now I'm going to get that again. It's not squared, but this is what I get. And then if I multiply the last together, you get S. Boom. And all of that's equal to 8. That's looking pretty messy, right? Could you do it? Yeah, you could finish solving that. Or would you rather see a different method that might be less messy or complicated? Let's look at another method. So let's change that and let's copy the problem. It was the square root of S minus 48. I think it was plus S, plus radical S, plus radical S equals 8. In the last example that we had where we only had that cube root, we isolated the cube root. Let's isolate the more complicated radical, which would be which one? That's not as complicated as the square root of S minus 48. So I want to isolate this first radical. So I subtract the square root of S from both sides. When you do that, the left-hand side becomes the square root of S minus 48. What happens on the right-hand side? 8 minus radical S. We can't group those two terms together. Now, how do I get rid of the square root? Right here. Square it. But if I square one side, you have to square the other side. What is the square root of S minus 48 squared? S minus 48. If I square the other side, keep in mind you have to take it times itself. So I got to multiply this binomial times itself. So the first multiplied together is 64. The outer is negative 8 radical S. The inner is going to be negative 8 radical S. And the last is going to be positive S. So negative times a negative is a positive. Question up to that point. That looks less complicated than that right there. Would you agree? Yes. So we're going to come back to this method, which it looks less complicated, and we're going to try to solve. Where would you go from there and solve it? I would group like terms together, which the left-hand side is already simplified. The right-hand side is going to become 64 minus 16, the square root of S plus S. Now I want to solve for S, and I have S actually occurring 3 times right now. Move the S over. So I'm going to subtract. Now why didn't that change? Now what is going on? My smartboard. Let's see if this. Why is it not selecting errors? There we go. Okay, I want to subtract S from both sides. What happens when you do that? The S's actually cancel in that as a constant or as a term by itself. So we get negative 48 is equal to 64 minus 16 radical S. Now I want to solve for S, and I have it occurring once.
You're making it complicated. Subtract 64.
Okay, we'll subtract 64 from both sides. Yes, you are correct. You could just flip-flop the sides, which means change the signs. So if you do that, you're going to end up with negative 112 is equal to negative 16 radical S. Divide both sides by negative 1, which makes it a positive there. Is that that's what you were technically trying to do? All right. Now what do you want to do? Okay, divide by 16. I'm just going to back up and say, look at both sides and divide by -16. What does that give you? Extend the page.
Radical S equals something.
The square root of S. Negative divided by a negative is a positive. I need 16. I need to multiply 6 times something that ends in a 2. 6 times what ends in a 2? 2, which is 12.
7,
6 times 7 is 42. 7 plus 4 is 11. So 112 divided by 16 is 7. Not divide by the radical. How do you get rid of a radical? You square it. You get rid of the square root by squaring, and I get S is equal to 49. But before you finish, since you started with radicals, what do you have to do? Check yourself. So we're going to go back to the very original problem, and we're going to check ourselves. So to check ourselves, let's do that in orange. S was what?
49.
49. So I get the square root of 49 minus 48 plus the square root of 49. Does that equal 8? Yes, it does. 49 minus 48 is 1. Square root of 1 is 1. 1 plus the square root of 49, which is 7. 1 plus 7 is 8. So is your answer 49? Yes, it is. Now you have 2 problems that are like that in your problem set. Number 8 and number 9. Numbers 5, 6, and 7 are like the first example that we went through. And number 10, I don't know if that's the exact one we worked through or not. So tomorrow, I am gone. I believe my sub